In Chapter 4, Section 3, we continue our discussion of probabilities, specifically of complement, conditional probability, and the Bayes theorem. The complement of an event is a subset of outcomes in the sample space that are not in the event. Let's consider the statement, of 10 adults, at least one of them has high blood pressure. The complement of this statement would be, none of the adults have high blood pressure. Conditional probability is the probability of one event occurring with some relationship to one or more other events. For example, if event A is that it's raining outside and it has a 30% chance of raining today, and event B is that you need to go outside and the probability of that is 50%. The conditional probability would look at these two events in relationship with one another, such as the probability that it is both raining and you need to go outside. And finally, the Bayes theorem is a way to figure out conditional probability. In a nutshell, it gives you the actual probability of an event given information about tests. In this section, we extend the use of the multiplication rule to include the probability that among several trials, we get at least one of some specific event. We consider the conditional probability, the probability of an event occurring when we have additional information about some other event that has already occurred. And finally, we provide a brief introduction into the Bayes theorem. When finding the probability of some event occurring at least once, we should understand the following. First, at least once has the same meaning as one or more. And second, the complement of getting at least one particular event is that you get no occurrences of that event. Let's look at the 4 steps of finding the probability of getting at least one of some event. First, we define A to be getting at least one of some event. Second, we know that the complement of A, or A bar, is equal to getting none of the event being considered. Step 3 is to find the probability of the complement of A, or A bar. In other words, we find the probability that A does not occur. And step 4, we subtract the results from 1. That is to say, we evaluate the expression, the probability at least one occurrence of event A is equal to 1 minus the probability of no occurrence of event A. Let's consider this example. A study conducted by Square Trade found that 6% of damaged iPads were damaged by the bag or the backpack. If 20 damaged iPads are randomly selected, find the probability of getting at least one that is damaged in a bag or a backpack. Is the probability high enough so that we can be reasonably sure of getting at least one iPad damaged in a bag or a backpack? Let's use our 4 steps to find the probability that at least one of the damaged iPads was damaged in a bag or a backpack. The first step is to identify our event A. So we say let A equal to at least one of the 20 damaged iPads was damaged in a bag or a backpack. The second step is to identify the complement of A. In other words, to identify A bar. We can say A bar in a few different ways. One way would be that A bar is equal to not getting at least one iPad damaged in a bag or a backpack. Or we can say A bar is equal to all 20 iPads damaged were damaged in some other way other than a bag or a backpack. Or finally, we can say A bar is equal to none of the iPads were damaged in a bag or a backpack. Now in step 3, we find the probability of the complement of A by evaluating the probability of A bar. So we say that the probability of A bar is equal to the probability of all 20 iPads being damaged in a way other than a bag or a backpack. Recall that the probability of A is 0.06. So the probability of A bar is equal to 1 minus 0.06. So we can say our probability of getting all 20 iPads damaged in a way other than a bag or a backpack is equal to 0.94 to the power of 20, which is equal to 0.290. And finally, the probability of A is equal to 1 minus the probability of the complement of A. So we can say the probability of A is equal to the probability of A bar, which is equal to 1 minus 0.290 or 0.710. So the probability of getting at least one iPad in the 20 that is damaged by a bag or a backpack is 0.70. So we can interpret this as, for a group of 20 damaged iPad, there is a 0.710 probability of getting at least one iPad damaged by a bag or a backpack. Although this probability is high, it is not so high that we would be reasonably sure of getting at least one iPad damaged in a bag or a backpack. So to be reasonably sure, we would want more than 20 damaged iPads in our sample. A conditional probability of an event is a probability obtained with the additional information that some other event has already occurred. The notation we will use for a conditional probability is P, open parentheses, event B, bar, event A, close parentheses, where we are finding the probability of event B occurring given that event A has already occurred. In the next few slides, we'll consider two approaches to finding a conditional probability, the intuitive approach and the formal approach. We'll start with the intuitive approach. So the intuitive approach for finding the conditional probability of B given A is as follows. Another way of seeing this is that the conditional probability of B occurring given that A has occurred can be found by assuming that event A has occurred and then calculating the probability that event B will occur. Now let's consider the formal approach to finding the conditional probability of P given A. The formula for calculating a conditional probability P given A can be found by dividing the probability of events A and B both occurring by the probability of event A occurring. So that is to say, the probability of A and B over the probability of A. Let's consider this example of pre-employment drug screening. We will use the table at the bottom of this slide to find the following. We'll find A, if one of the 555 test subjects is randomly selected, find the probability that the subject has a positive test result, given that the subject actually uses drugs. That is to say, find the probability of a positive test result given subject uses drugs. If one of the 555 test subjects is randomly selected, let's find the probability that the subject actually uses drugs, given that he or she had a positive test result. That is, we will find the probability that the subject uses drugs, given positive test results. With the intuitive approach, we want to find that the probability of B given A is equal to the probability of a positive test result given the subject uses drugs. If we assume that the selected subject actually uses drugs, then we are dealing with only 50 subjects in the first row of the table. Among those 50 subjects, 45 had positive test results. So we get that the probability of B given A is equal to 45 over 50, which is equal to 0.90. Now for part A, let's use the formal approach. With the formal approach, the same results can be found using the formula probability of B given A, where B is a positive test result and A is equal to the subject's use of drugs. Using the formal approach, we first want to find the probability that the subject uses drugs and had a positive test result. That is 45 divided by 555. Next, we want to find the probability that subject uses drugs, and that is 50 divided by 555. We get the 50 by totaling the first row of subject uses drugs. So we add 45 for the true positive plus 5 for the false negative. And finally, the probability of B given A is equal to the probability of A and B divided by the probability of B. And this becomes the probability of a positive test given the subject uses drugs is equal to 45 divided by 555 over 50 divided by 555. Now remember, your 555 on the numerator and the denominator will cancel out, and that gives you 45 over 50, which is equal to 0.90, which is the same answer we got using the intuitive approach. So by comparing the intuitive approach to the formal approach, it should be clear that the intuitive approach is a much easier way to calculate the conditional probability, and it is less likely to result in errors. Let's recall part B for the pre-employment drug screening problem. If one of the test subjects is randomly selected, find the probability that the subject actually uses drugs given that he or she had a positive test result. So here we're going to find the probability that the selected subject actually uses drugs given that the subject had a positive test result. If we assume that the subject had a positive test result, then we are dealing with 70 subjects in the first column of the table. Among those 70 subjects, 45 used drugs, so we can say that the probability the subject uses drugs given a positive test result is equal to 45 over 70, and that's equal to 0.643. We can interpret these results as follows. With the first result, or part A of our example, we can say that the probability of a positive test given the subject uses drugs is equal to 0.90, and this indicates that a subject who uses drugs has a 0.90 probability of getting a positive test result. With the second result, or part B of our example, the probability that the subject uses drugs given the positive test result is equal to 0.643, and this indicates that for a subject who gets a positive test result, there is a 0.643 probability that this subject actually uses drugs. So in the prior example, the probability of a positive test result given the subject uses drugs does not equal to the probability that the subject uses drugs given a positive test result. This example proves that in general, the probability of B given A does not equal to the probability of A given B. There could, of course, be individual cases where the probability of A given B and the probability of B given A might be equal, but in general, they are not equal. To incorrectly think that the probability of B given A and the probability of A given B are equal, or to incorrectly use one value in place of the other is called confusion of the inverse. Let's consider these two events. Event D is that it is dark outside, and event M is that it is midnight. In this example, we're going to ignore anomalies like an Alaskan winter, where daylight hours can be as few as 4 hours a day. So let's consider a couple of probabilities. The first probability is the probability of D given A is equal to the probability it is certain to be dark given that it is midnight. This is approximately equal to 1. The second probability is the probability of M given D is equal to the probability it is exactly midnight given that it is dark outside. This is approximately 0. So you can see that the probability of D given M does not equal to the probability of M given D. We refer to this as the confusion of the inverse. Confusion of the inverse occurs when we incorrectly switch those probability values or we think they are equal. We extend the discussion of conditional probability to include the application of Bayes' theorem or Bayes' rule, which we use for revising a probability value based on additional information that is later obtained. Bayes' theorem is a way to figure out conditional probability, and it gives you the actual probability of an event given information about the test. Let's consider this example of interpreting medical test results. Assume cancer has a 1% prevalence rate, meaning that 1% of the population has cancer. Denoting the event of having cancer by C, we have the probability of C equals to 0.1 for a subject randomly selected from the population. Using data from a study in the Cambridge University Press, the result is included with the following performance characteristics of the test for cancer, where the probability of C is equal to 0.1. That is to say, there is a 1% prevalence rate of cancer. Also, the false positive rate is 10%. That is to say that the probability of a positive test given that cancer is not present is equal to 0.10. And finally, the true positive rate is 80%. That is to say that the probability of a positive test results given that the cancer is present is equal to 0.80. Now let's find the probability that a patient has cancer given that they have a positive test result. We can represent this as the probability of C given a positive test result. Using the given information, we can construct a hypothetical population with the characteristics we described in the previous slide. Let's assume that we have 1,000 subjects. With a 1% prevalence rate for cancer, 10 of the subjects are expected to have cancer. The sum of the entries in the first row of the values is therefore 10. The other 990 subjects do not have cancer. The sum of the entries in the second row of values is therefore 990. Among the 990 subjects without cancer, 10% get a positive test result, so that 10% of the 990 cancer-free subjects in the second row get the positive test results. And you can see the entry of 99 in the second row that show a positive test result. For the 990 subjects in the second row, 99 test positive, so the other 891 must test negative. And so we can see the entry of 891 in the second row. So note that 990 minus 90 equals to 891. Recall that the true positive rate is 80%. Among the 10 subjects with cancer in the first row, 80% of the test results are positive. So 80% of the 10 subjects in the first row test positive. And so we can see in that cell there's an entry of 8. The other two subjects in our first row test negative. So you can see we have an entry of 2 in our first row under the negative test results column. Now that we have an understanding of all of the elements for our table, let's find the solution to the probability of having cancer given a positive test result. The positive test result column in our table includes values of a positive test results whether or not the patient has cancer. So in that column, the probability of randomly selecting a subject with cancer is 8 out of 107, or 0.0748. So we can say that the probability of having cancer given a positive test result is equal to 0.0748. For the data given this example, a randomly selected subject has a 1% chance of having cancer. But for a randomly selected subject given a test result with a positive result, the chance of having cancer increases to 7.48%. Based on the data given in this example, a positive test result should not be devastating news because there is a good chance that the test is wrong. A prior probability is an initial probability value originally obtained before any additional information is obtained. A posterior probability is a probability value that has been revised by using additional information that is later obtained. Relative to the last example, the probability of having cancer is equal to 0.1, which is the probability that a randomly selected subject from the population has cancer. So the probability of having cancer is an example of a prior probability. Using the additional information that the subject has received a positive test result, we found that the probability of having cancer given a positive test result is equal to 0.0748. This is a posterior probability because it uses additional information of the positive test result. This is the end of Chapter 4, Section 3. Please proceed to Chapter 4, Section 4.